Hello. Hi, guys. My name is Nikola Sijakinjic, and I come from the Belgrade office of Incor. I'm here to talk about the Hazlecast. Actually, to talk about tools we use and with Hazlecast, like Redis, the in-house NPI. Idea to explain this to wider audiences, and hopefully, if you like it, maybe some of you can join me after the talk in lobby and we can discuss it. We're currently looking for developers working on these subjects. So, what is Hazlecast? It is in-memory data grid. Well, data grids are kind of fancy buzzword, and I had a hard time looking for a proper fancy definition. The best I got is this from Oracle, and it kind of says it all, but it doesn't state much. Actually, you can place a lot of in-memory tools under this umbrella, and maybe it will be easier to say what a data grid is not. Well, this represents the split of these tools into three categories. On the simplest side would be distributed caches. These are simple key value stores. They can execute only CRUD operations and nothing more. And on the other end, we will have in-memory databases. These are full-featured in-memory relationship databases with all notions like primary key, foreign key, table, etc. And somewhere in between, there would be in-memory data grid. Basically, it's kind of like distributed cache on steroids, have some processing power, some interpreted language. In our case, Lua or Java, but Golang is currently also popular. And they've been used for quite some time, like 20 years or something, like 10 years. Mostly, I mean, by financial institutions and telco industry, because they were the only ones who had needs for this kind of tools. And since we went to the cloud, this became popular among the common people, common engineers. Okay, so why would we use these tools? I mean, does it make sense, like, to spend some buck on Hazlecast or Redis or Coherence or something like that? Well, we should look at the scenario in which we are failing to provide user experience. Time ago, the critical issue we were facing was the time. We needed fast responses, but today in cloud, we're not only concerned about the time, we are concerned about the key resources we may lack, like three critical resources from Neumann architecture, like memory, like CPU, like network. And this may be like the physical boundaries we can't pass in a monolith applications. Well, since we're probably making a wrap in Java, additional issue we face is garbage collection. In a like simple Java app, 3 gigs of RAM, and you call system GC, you can. I mean, I can expect in my tree box that it will last around 30 seconds. For 30 seconds, well, not 30, but almost 30. 30 seconds, the app will be frozen, absolutely. I mean, unresponsibly, totally. Maybe system GC is not kind of even that occur in a runtime, but you can see the graph. This is GC viewer for the box that's used in development, running 24 hours a day, and it's not much. It got 1 gig of RAM. And with the green fields, here you can see that minor GC units occur roughly once a minute, and they last for 50 milliseconds. I mean, that's not a big deal. I mean, especially if you're doing a web app. But if you look at the red ones, these are the major G events. And these are like scary results because on average, they last 8 seconds. With one outlier, that's 18 seconds. And during this time, I mean, user literally can like pick another app and download it and find an info he asked for. And I mean, there are a number of ways how to pass this around. One of the most popular is to use direct memory tools like EHCache, which is pretty popular. I'm sure if you've used Java, you've used EHCache. He stores data out of the heap into direct memory, so job for garbage collection is significantly smaller and therefore shorter. Some other guys who are like interested mostly in time, like in fast responses, they use this is like proprietary Java runtime, Zing's Zulu, and it is actually a runtime that has a proprietary garbage collection that is running continuously in the background, but it also has some drawbacks. I mean, it is shockingly fast. You don't have the stop the world events, but it needs a lot of it needs to do a lot of work if your heap grows. I mean, a lot. Your premium CP may behave like a cheap one. What we do in ThinkWar, and what most of the people who who currently do are microservices, they move the state out of the application. And in the picture on the left, we see like some theoretical JVM that contains tons of the data and like 10 gigs of RAM. In this situation, GC may be significant impact. Also, like cloud price for this app may be significant financial impact. If we move the state out of the service, like in a picture on the right, maybe it looks like kind of silly to do because something that's basically in the reach of our hands now require a network hub. But if we do that, there are some like really significant benefits we can use in this case. I mean, especially if you look at the services. I mean, it's kind of simple. Services take a lot less memory than in a monolith app. So we can place them in actually in micro Amazon instances. These are the cheapest box available. Also, this table should this is the 1 year old table. The prices are not such, but this is definitely the case. These all 4 lines are actually the same computing power bought from the Amazon. And the first line represents the 8 boxes with single core. And it costs $76 to run on a month. And the bottom 1 row represents the single instance with 8 cores. And it costs like 5-fold more. I mean, this is a huge financial impact on running your services. Also, these services are now stateless, so we can use functional languages like Haskell, like Erlang, or I don't know. And I mean, they're quite a performant. WhatsApp is using like 20 computers to run like 700 million users And I don't think that it's possible with kind of architectures in like Java or PHP or I don't know. Also, I mean, there are a few interesting points on high availability. You see, we can lose one of the services boxes, and user experience may be like slower, but eventually the app will still work. And also, in a moment of like user surge, when we need like 10 boxes, we can like pull the volume, like turn the volume up and reserve like 10 instances and serve the content. When they are gone, we can reduce the bills by returning to like 2 instances. And these are pretty cool stuff, like having for our services. The question is, can we do like this similar thing to machines that running state? Like in a picture above, these HZ represent the single node. There are 4 of them. Each of them represent a single node, and every cache is distributed across all the nodes. How can we provide the same features to our system like in services? First, yes, we can fine-tune the prices for our boxes. Second, high availability, elasticity is provided by itself. I mean, both Redis and Hazlecast allow us to like easily add a new box to the grid. But the thing with the state is that it's really hard to provide same availability and resilience to the failure. Actually, there are a number of ways how to deal with it, but almost everybody has some kind of fault. And Redis, an example, Redis came out with the Redis cluster. It has a notion of master nodes and backup nodes. You can't run cluster without with less than 6 nodes. So it means they have to run 3 masters and 3 slaves. And if one of the masters fail, the slaves are promoted to masters, and we have provided some kind of availability. But this is a tricky part, because the only way how to back the data in Redis is to do it asynchronously. And if it means that master node will wait for some time until the batch is ready to push to the backup. If server fails in that time, this data is lost. And Redis itself does not guarantee strong data consistency because of that. There are some ways how to deal with these issues, but this will performance will not shine like it is in a regular use case. On the other hand, Hazlecast has a different approach, and it's having architecture where all nodes are equal. Basically, every node is master to some portion of data. It is represented with the blue rows. The columns are the nodes, and we can see that in an upper table, in a healthy state, node number 4 is alive. And he backed all of his data to the nodes number 1, 2, and 3. In the case of hazard, the number 4 will fail, and the nodes and the pieces deployed in the other nodes will be promoted to master data, and city will rebalance itself to the healthy state again. I mean, this also have some drawbacks, like we can afford to lose only 1 instance, and we must reserve enough space. The volume for the data at start should be acceptable to accommodate the same volume data in the hazardous states. We can see in the upper table that there are white rows. These are the empty rows, and there are no rows. There are no empty rows in the situation below. So none of them are like truly great at and fault tolerance, but they give some solution to it. Okay, so we see that like Hazlecast has some bad sides. Let's see the good sides. Well, Hazlecast is probably not the best, the fastest thing to have because it was made to be easy. I mean, and it is very, very easy. And the most important thing I would like you to take home after this lecture is just that, to know that Hazlecast is really, really easy to use. And these three lines are actually creating a single node. This is the first line. The second line is creating a map. And the third line is inserting in this map. And this app will create one node. If you run three nodes in the same LAN, they will automatically sniff each other out like over the multicast, and they will join a cluster. And that it is that easy to start with Hazlecast. I mean, it doesn't mean that everything is easy with Hazlecast. There are some tricks you should know about, like configuring threads, number of threads, and how to use it. I mean, it's not a science exactly, but you just can't move as you wish. Also, what's bad with I forgot to say that I mean, holding data in Java is kind of insane because I mean, Sun made Java and they were a hardware company. They didn't care much about the data, about the hardware, and if they could sell you like gigabyte of RAM, sure they would. And Java is pretty, I mean, insatiable when it comes to RAM. You see that one integer in Java that has like 3 pointers to it. Actually, one instance takes about 128 bits, maybe less, but around 128 bits. And that's a real lot. I mean, it doesn't make sense to store this info this way. So they had to do something about it, and data is never kept, I mean, never kept. The rule of thumb is to hold data in a serialized form. Maybe, I mean, it will be better to process, for processing, to have it in an object form, but if you do a lot of gets and puts, you're not interested really in object itself, you're interested in serialized form. And if you kept it in serialized form, you can flush it easily to network, and you don't have to waste your time serializing and deserializing objects. Also, if you need a lot of processing, you can use object format. And if you're somewhere in between, you can use best of the two worlds, like cache. These are the keys that were frequently used, and they are served as objects for processing. Okay, so there are a few differences in architecture between Redis and Hazlecast. Actually, Redis is way faster. If your operations are crude, Redis will nail it. I mean, like pretty much. I mean, I think it's 2 times faster than Hazlecast, but it much depends on the way how you use it and how much writes you do. That's quite trivial thing to say that Redis is like twice as faster. On the other hand, where Hazlecast shine, that's the processing. I mean, Redis started as a distributed map, and eventually he got so many features on processing that we can call it data grid. And these are some of the distributed primitives. I mean, this is just to show that they're almost exactly in Java. They're just distributed, like the names and types. They do the same things. The one we are most interested in are collections, distributed objects like lists, like queues and topics. We use this oftenly. And the most interesting structure of all, and the only one that is truly distributed, it spans across all nodes, is IMAP. And there is a number of, and the most of functionalities provided are exactly related to the distributed map. We have, as in Redis, like partition control when we want to like process the data. Sometimes some data should be like near each other because we want to aggregate them. It doesn't make sense to ask two nodes and make like 3 or 4 network hops. If we can place the same data, group them and place in the same partition for processing. In that case, we will get like just 2 hops, like request and response. And that's this partition control and data affinity. And it's like, there's some better, I think that Hazlecast stands better than Redis on this subject. Also, when it comes to processing, you can always like remember that you're using the backups from other nodes in your local, and you can use that info for aggregation. Okay, when you use maps, I mean, if you supply them with caching algorithms like last frequently used, I mean, they become caches, and that's that's something that's Hazlecast known for also. I mean, Hazlecast is the first project that implemented JCache. That's JCR Java standard for caching solutions. And to me, the most important, I mean, in FinCore, the most important part of the feature for map are these near caches. I mean, in our system, like we have like 2 kinds of data. Well, some data that is used for presentation, like we call them like loose data, that's kept in data grid, and some data that should like leave a trail, like payments and that would make transactions. These are important data, and we mostly read this loose data. Services mostly like get the prices, compare them with I don't know current situations, and do not hustle. They do not make pressure on database. So it makes sense to use like near cache for reading the data. If your keys are significantly skewed and some of them are often used, this near cache can provide significant impact, like on performance. In our case, it's like 20% less network hops for our services. Maybe, I'm not sure, maybe this can be done in Redis, but I mean, you'll have to struggle with it. Also, when you when you're processing and you want to do something in transactional way, I mean, you can always opt for optimistic locking. It may lose you like a few hops if needed. And when it comes to processing, this is the place where Hazlecast shine. Actually, the main difference between Redis and Hazlecast is, from some reason in Redis, the scripting is not bad, but the Lua, which is used for scripting, is kind of far away from the data. And you'll see an example later that reading 1,000 values from Lua is way slower than reading 1,000 values from Hazlecast. And in order to like provide us these scripting features like processing and logic, the good guys from Hazlecast provided DSL, Java as a DSL. First, JVM is a state-of-the-art virtual machine. It is fast enough. I mean, probably the fastest virtual machine. Also, there are a lot of libraries you can use, like jQuantlib, or if you're in finance, or I don't know. If you are into like fast processing, like few entries, there's Enter Processor. You can send it, and the same thread that is practically reading the data is actually changing it. We have aspect programming, support for aspect programming, interceptors and listeners. That's not available in Redis. And executive service, this is the main thing. This is the distributed thread pool where you send your basically requests when needed. And if you want to calculate your current exposure to risk, in Redis you will have to get all the keys and sum them. In Hazlecast you can use this mechanism like executive service to send the logic to the grid, and they will aggregate it in a distributed way and return it in no time. Well, these are some of the tests we made in-house. Actually, for this product, we chosen Redis as a main tool. But we are using Hazlecast in some other tools, mainly publishing. This NPI daemon, this is our in-house solution similar to Redis. Actually, it is made a long time ago. If you look at the numbers, it looks like it is... oh yes, here we try to insert 1.5 million of entries in every of tools, and we see the Hazlecast is kind of slower, like 2 times, and it looks like his NPI ID is also lagging behind. But don't be fooled. The thing is that NPI is like our old system that will pass, that will be rewritten, and currently it does not support the bulk loads. In these use cases, we were sending like hundreds of elements at once. First, we would wait to fill the batch, like 100 elements, and to read the batch, and then send it to the Redis or Hazlecast. But in NPI daemon, we can only send a single key value at this very moment. But this will something that soon we're going to change. So when you look at the results, 6 seconds against 4 seconds, this actually means that NPI is not slower like 2 times. It means it is faster 50 times, because he's doing single writes. He's doing 100 single writes instead of 1 of 100. And when this change, NPID will bleed for a length. But NPID is quite simple compared to Redis. Redis is nice because it's simple enough and got some additional features and scripting and pub/sub and everything. So when we look the results, I mean, Hazlecast pretty much lags almost everywhere by half. That's because we're not doing any processing. If you're interested in testing your performance of Hazlecast yourself, the Hazlecast guys opened their stress testing tool to all of us. So if you're interested in testing in cloud or in your like in-house environment, you can use it to easily deploy it. And there are a number of tests. But these tests are simplified, and I mean, you should, if you're interested, you should like take to account all key aspects of your architecture. Like, do you have like roll writes from outside, or how many writes? Like, is it like 99% are writes and one is a read, or it's other way around? And there is this is a picture that depicts like the workflow. At the top is a simulator that runs. They orchestrate all clients and nodes, and below there are nodes running in Amazon Web Services. The idea was to show you like how it's deployed, but then I realized that the network bandwidth is pretty much limiting, and we wouldn't make it in this session. But if you're interested in the difference between processing between Hazlecast and Redis, yeah. And this is too heavy for me. I don't have a mirror image, so and I can't mirror. Maybe it would be, if some of you guys are interested in these kind of things, maybe it would be good to find me in the lobby after this talk. Well, when it comes to processing, I had a really hard time looking for like the common ground for these two, because Redis is strikingly fast, and like Twitter is using that to like manage number of millions of users. And Hazlecast is more like a general purpose tool. So comparing them is like comparing SUV to Formula. Like Formula is fast, and it will nail the SUV on a track. But if you have a bumpy ride or go over the sand, there's no way it can deal with that. In my results that I can't provide that right now, maybe later in lobby, somewhere about like 500 keys. It's if you process more than 500 keys in Redis, it will become slower than processing them in Hazlecast. They are there's some like border when it makes sense when to use Hazlecast rather than Redis. If you use like single K operations, Redis will always be faster. I hope you like these kind of things. We currently have quite a few open positions, and if you're interested in that, you can find me in the lobby, and that's it. Thank you for your time. That will be it.